Work is the change in energy experienced by an object. Two people can do the exact same amount of work, but one person can be way quicker than the other person. It doesn't change the amount of work that's done. Rather, it changes the rate at which work is done. We define the rate at which work is done as the power output of something. So if we had two people shoveling their driveways next to each other, the work that they would do in shoveling the snow out of the driveways would be the exact same amount of work. If one person did it in 1 hour and one person did it in 4 hours, the power output of the person doing it in 1 hour would be higher. The work done is the same, but the rate at which the work was done would be higher. Now, if power is defined as the rate at which work is done, then the equation that would describe power would be work over time. Work in joules, of course, divided by the time in seconds. What do you think the units for power would be based on the equation that you see up on the board? What is it? Joules per second works, yeah. Power is measured in joules per second. But another set of units is the exact same meaning as a joule per second. What do you think that unit is? What do you think that other unit is that is the same thing as a joule per second? What do you think it is? I'm giving you the answer and you can't even hear it. What do you think that unit is that's the same as joule per second? No, that's, well, a joule per second is the same as a joule per second. Yes, it is. Watt is the same as joules per second. What is it? Watt is the same as joule per second. 1 joule per second is equal to a watt. Now, you got to be careful here. Work, the symbol for work is W. The unit is joules. The symbol for power is P. The unit is W. These two W's mean completely different things. This is work in joules. This is power in watts. If you prefer to use joules per second instead of watts, that's okay, because they mean exactly the same thing. Now, I'm also going to express this equation a little bit differently, even though this is the way that it appears on our data sheet. Because of the work energy theorem, we know that power could also be equal to delta E over T. Right? W is equal to delta E. In the end, when you're solving one of these power problems, what you got to do first is solve for work using the method that we learned over the last couple of days, and then divide it by time. That will give you the rate at which work is done. That will give you the power. Now, instead of giving you the typical example problem that I give you, today we're going to do it a little bit differently. We're going to set up a little activity where you're going to measure the power output of your legs. Now, we talked about this a little bit yesterday, but I'll just refresh your memory on how this is going to go. Instead of saying example number 1, blah, 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 let's solve it. Example number 1 today is, what is your power output? What is the power output of your legs? Now, how are we going to do that? Oh, we're going to say power is equal to work over time. The power output of your legs is work over time. As you climb up a flight of stairs, you will measure how much time that it takes to go up that flight of stairs. So that's easy, right? That's easy to get T. Just use a timer on your phone to measure how long it takes you to go up those flight of stairs. Measuring the work that you do as you go up those flight of stairs is a little bit harder, but it's still not that hard. Work is equal to F times D, but work is also equal to delta E, the change in energy. Your change in energy as you go up that flight of stairs, what kind of energy do you have after you've made it to the top of the stairs and then you're panting at the top of the stairs, standing there waiting for the next person to go? What kind do you have now? You got potential energy, right? Because you're at the top of the stairs. Your final energy is potential energy. What's your initial energy? Is you're standing there waiting to press start on your phone, waiting to start running up those stairs. What's your energy? 0. So we'll say final energy minus initial energy. mgHf minus 0 is equal to delta E, which is equal to W, divided by T. If you know your mass in kilograms, G, of course, is 9.81. The height of the stairs, I told you yesterday, is 3.0 meters. Multiply those together, divide by how long it takes you to go up the stairs in seconds. You should get your power output in joules per second, which, of course, is the same thing as watts. Make sense? We're going to go out to that flight of stairs in just a moment, but before we do, I want you to commit to a prediction as to what your power output is. If you're wrong, it's fine. I just want to know what you predicted and what it actually is. So the power output of your legs in watts or in joules per second, write it down on a piece of paper so that you're committed to it, and give that piece of paper to somebody else so that you can't go and change it once we get back and have the actual value, all right? Got it? Now, you get a couple of options here. You can walk up the stairs and find the power output of your legs at a particular moment in time as you're walking up the stairs. Or you can run up the stairs as fast as you want, as fast as you can, to measure the maximum power output of your legs. There's a couple things, though, that you can do and a couple things that you can't do. Skip stairs? I don't care. Be my guest. Okay, skip stairs if you want. One stair at a time, whatever works best for you. Do not use your arms. You can't hold onto the rail. Otherwise, you're not measuring the power output of your legs. You're measuring the power output of your legs and your arms. It has to be your legs that does the work. Now, the other thing to remember is this. Two people may run up the stairs and have exactly equal times. That doesn't mean they're going to have the same power output. Okay, one person's time is 2.5 seconds, the other person's time is 2.5 seconds. Doesn't mean they're going to have the same power output. What else affects it besides the time? Yeah, the amount of work that you have to do. And the more you weigh, the more work you have to do. Okay, does that make sense? Now, again, run up the stairs, walk up the stairs, I don't care. Measure your power output, that is your current power output or your maximum power output. I don't care. Just make a prediction based on what you plan to do, and then go out there, do it, and see how closely it matches the prediction. All right, we've gone through this, and we've got a range, I think, of 100 and something watts of people walking up the stairs to 937 watts, people running up the stairs. One thing that I want to point out before I set you free on these questions is that, like, when we see 937 watts, that's a high power output. 1 horsepower is defined as approximately 750 watts, which means that if you had more than 750 watts, that means that technically, for a short period of time, for 2 or 3 seconds, you're stronger than the average horse. Now, I suspect that you can't maintain that as long as a horse may be able to maintain that, but for those 2 or 3 seconds, then you're as strong as a horse is. All right, we got a few questions on worksheet number 4. What I'd like you to do is, there's 7 of those questions. I'd like you to do the first 5 questions on worksheet number 4, please. Questions 1 through 5 right now. Now let's take a look at question number 4. It says an 1100 watt microwave oven is turned on for 2 minutes. What's the energy consumed by this microwave oven? This is a power question. This should say 1100 watts, right? But I told you before you worked on it that that's what it was supposed to be. The power is work over time. We want to solve for the energy used up here. Well, work is equal to delta E as well. So power can be delta E over T. If we rearrange that to solve for delta E, right, the T goes up by multiplying, and it becomes power times time. That means it's 1100 watts. But what do we got to remember to do here with the 2 minutes? Convert it to seconds, right? In 2 minutes, we multiply that by 60 to get the number of seconds here, which is 120 seconds. So 1100 watts times 120 seconds gives me 1.32 times 10 to the 5 joules. Does that make sense?